T-test for independent groups. This is sometimes also called an independent samples t-test. This is probably the most common statistic, inferential statistics, that is used in all of psychology. Remember, a t-test is used with only a single factor. You have a dependent variable that's of interval ratio, or you can calculate a mean of it. And you have only two levels, control group and experimental group. So we have two samples here. We're not comparing a sample to a population. We have one sample compared to another sample. In this example from the lesson, we're going to talk about this breast cancer drug, Herceptin. We're going to use this experimental drug to see if we can reduce tumor size in patients. So we have 100 people, 100 cancer patients that are all within the same stages of their cancer treatment. And in half the group, or 50 subjects, we're not going to treat them with anything, and the other half we're going to treat with this experimental drug. And then we're going to compare the results of the dependent variable, hoping that the dependent variable will be reduced in this case if tumor size is reduced. So this is a classic t-test for independent groups, or independent samples t-test. Here's our formula: the mean of the sample, the first sample, minus the mean of the second sample over the standard error of the difference. Now this one's got a formula right here that's a little tricky, so let's take some time on this. It's got these very strange looking components here. This is not meant to confuse you. This is just the standard error of the first sample squared and the standard error of the second sample squared. We add them together, take the square root, that's how we get standard error of the difference. To simplify things, remember that standard error is just s over the square root of n. So I changed this formula around a little bit to s1 over square root of n1 squared plus s2 over the square root of n2 squared. All these variables we have, they're given to you in the problem, right? So the standard deviation of the control group, 1.19, for the experimental group, 2.11. We know that the 100 subjects were split in half, 50 to the control group, 50 to the experimental group. So there you go, we have our numbers. Take the square root of 50, divide by the numbers, and then square them, and then add them together. And here is the standard error of the difference for this formula, or the denominator of this formula right here. So we put our two means in here, the mean of the first sample, 22.45, mean of the second sample, 16.05, and then we put our standard error right there. And we do this simple math, 6.4 over 0.342, we get a t-value of 18.71. Next step is calculate degrees of freedom. Here the formula for degrees of freedom is n1 minus 1 plus n2 minus 1. We know that n is 50 in both conditions, so it's going to come down to 49 plus 49, or degrees of freedom of 98. So now we go to the t-table to look for the critical value and see if we've surpassed it. We know this is a one-tailed test again because we're predicting direction. We want to reduce tumor size. So we're going to look for a one-tailed test, a column of 0.05, and we want to go down to the degrees of freedom of 98. Well, if you do that in a t-table, it turns out there is no actual number 98. So what you want to do is you want to go to the one closest below it. Okay? And when you do that, you find a critical value of 1.671. 1.671, and since our t-test was 18.71, we can say indeed that we have significant results. The Herceptin drug did significantly reduce breast cancer tumor size. That's how you do a t-test for independent groups, or it's also called an independent samples t-test.